Hi, everyone. I'm Jay with UNStudio. I'm here with a really amazing team coming from Austin and New York. We're joined with Walter P. Moore, really great guys, and thank you again for hosting this awesome event. It's been a lot of fun and a lot of learning. And it really brought us all together to really hang out and work together. Great facilities too, by the way. Thank you. We're missing Franz and Laura today, but together we form a really integrated team that does not a lot of analysis, pushes the limits of what's possible with Terra, but further, enhances the built environment and things that we can do with it. So, just quick summary. I'll just give a brief intro to about UNStudio, pass it to Gustav and Jake, talk about Walter P. more briefly, and then we go into the project and the design itself. So, at UNStudio, we always aim to create meaningful places, and that's always depends on the context itself, because of course there's different scales that we're looking at, whether they're bridges, towers, cities, or even products, to create a lasting impact. And to kind of do that, the context, of course, is very important, and that context can depend. For example, it is at the level of a product. So for ACAW, we are really kind of pushing previous studies we have done, for example, at the WasI Tower with ceramics and terracotta, and other projects to really test the limits and push the boundaries of what we can do and achieve through geometry, and also study the analysis to see what's possible and how it can affect the environment and vice versa. With them, maybe
Thank you, Jay.
Yeah.
Hi, everyone. I'm Gustav Parksner with Walter P. Moore. My colleague Jake Leventhal is over there, and Laura Carnath in our LA office is supporting remotely. We've had the great pleasure of working with the team UNStudio for this workshop. This is our company. For those who are not familiar, we're a national international firm of about 800 people. It's 700 plus, so that actually 800. Structural and facade, civil engineers, several other disciplines. We're coming out of the New York and the LA offices, and we have a fairly large amount of offerings, which I won't really go into right now. We'll talk about that later if anyone's interested. And we also do a large array of projects, just like UNStudio, trying to kind of pay a lot of attention to placemaking, the human aspect of design and details. Even though a lot of the things we work on are very large, that doesn't mean that they need to be overwhelming. And sometimes we also do things in terracotta when we can, happily so. Here at ACAW, we've participated several times with many people that are here now and many people that have been here in previous years. Always enjoy doing whatever is thrown at us and sort of run with it. So I'm handing it back to you, Justin.
Thank you. So yeah, I'm Justin with UNStudio. So this is really the high-level problem where we wanted to start with. Our cities becoming hotter, more polluted. Even just the operations of building alone contributes to 27% of the global emissions. And we want to change that. So we look to facades because it's the largest surface area of the building. That seems to be the largest opportunity for change. So our proposal here comes with a threefold approach. First we're looking at the form of our terracotta facade system. So how can the form be manipulated in such a way to maximize efficient passive cooling? And we'll go into some of the inputs that drove the form that you see here. And then the glaze. So terracotta is an inherently thermally performing material, as we know, but how can the glaze become a part of that thermally performing possibilities as well? So then the attachments as well, how can we design the system in a way that has a minimal attachment system to, of course, reduce the embodied carbon of the overall system? So we're dealing with operational carbon, embodied carbon in the combined way. So yeah, first looking at the form. So jumping off point for our project is the WasI Tower, as briefly mentioned before. This is a project that we've designed. It's under construction now in Dubai. It is one of the tallest buildings that incorporates a terracotta facade. And WasI Tower is designed in such a way to maximize or to reduce the solar heat gain on the building. both in the form of the overall building, but also in the arrangement of the fin system that you see here on the left. So there's been, as we designed, and there's all kinds of solar analyses that are done to show how can we arrange these fins, these terracotta fins, in a way to reduce that solar heat gain. And here's a close-up of what that looks like on the left. This is, you see the kind of burnished terracotta glaze pattern here and its attachment system. So it really works as a kind of car grill, really. So it takes on heat during the day, and by spacing it a bit separated from the building facade, it allows wind to move behind it to cool it off in the evenings as the sun is reduced. So here's some close-up views of how that's being installed now. So throughout our process, we're looking at different ways to push the boundaries of what a fin system can do in reducing the heat gain on the building. So there's a bunch of different factors that we started to tease out from these studies. It's about minimizing solar heat gain. It's about minimizing the attachment system. It's about maximizing visibility from the inside of the building as well. How do you optimize daylight with the form? And a big component of this as well is how do you maximize the fabrication constraints of the terracotta? So as we know, in a kind of typical curtain wall that's perhaps fully exposed to the sun, you have a lot of solar heat gain that happens. You look at how fin systems work, and they are successful in sort of reducing some of that solar heat gain onto the building. But we wanted to see how we can take that a bit further in our proposed system to manipulate the geometry to protect the building even further from the solar heat gain. And then we have other ideas about integrating ceramic frit as well to even further reduce that. And then minimizing the attachment system. Typical rain screens and facades, typical fin systems might have multiple connections, but how can we really, maximize both the fabrication constraints in this proposed system to minimize that attachment system? So, in our system, it's really only connected top and bottom. But also, an important aspect of it is the visibility from inside of the building. So how can a form be done in such a way that allows for views through and behind the fin system as well? And optimizing daylight. Of course, we want to allow light into the building. And how can the form be adjusted in such a way to maximize daylight deep inside of the space of the building? So that's part of the drivers of our form. And I've mentioned it, maximize the fabrication constraints. This is what we've worked with Boston Valley with, trying to push the limits of. So the maximum extrusion length, what we see on our mock-ups, is a 6-foot length, trying to maximize the width as well. So taking all these different factors that are drivers of our form, putting them together, arrive, and then we bring in an element of the twist. So this is a formal typology that incorporates many different functions. For instance, on the project you see on the left, it's about reducing the amount of columns in the space, but also allowing light into the space. It's a wayfinding element. It incorporates circulation. So we like these formal moves that incorporate lots of different performative elements. And that's how we arrive at our forms. This kind of overlay of all those different inputs of the form. Also seeing, how we've done this in elevation and plan. So this form was done by, we extruded the maximum length. We designed a form system that was then slumped onto. So the form system is made out of terracotta as well. And the weight of the extrusion allows it to slump into the form to arrive at this twisted form you see here. And a big part of that, minimizing the attachment system is, how is this form stable and structural on a building application? So that's what Jake's going to tell us a bit about.
So as Justin mentioned, part of the intent of this is to absolutely minimize as much metal on the project as possible. And so in order to do that, we took it upon ourselves to try to optimize the amount of load that we are demanding that the terracotta itself takes. But because of the unique form of this, because there's so much susceptibility to this system wanting to twist and rotate and flex in somewhat unpredictable ways because the way the fin curves and how it is projected off of the building, especially on a building like the WasI Tower, where it goes quite high and twists around. We wanted to be as safe as possible. So the first thing we did is set a pretty low floor, or a low ceiling rather, for what we wanted to allow the terracotta to take. So using some of the data that's provided by Boston Valley, we tried to normalize this to take into account as much of the variation in the testing as possible to minimize any of those potential variations from causing a problem on the project. And then separately after that, we applied a very high and rigid safety factor to the allowable stresses that we were going to see to make sure this is as safe as possible. I think in the future, we could probably refine this and reduce that. But for the purposes of this, we wanted the proof of concept. And even with what we wound up finding, we set up a pretty detailed finite element analysis of this, and we ran this with wind hitting these systems in multiple angles, multiple directions, trying to twist, pull, and flex this in as many ways as possible. And ultimately, what we're able to find is, thanks to the strength of the terracotta itself, and also due to the internal structure of the webbing, it actually allows this system to perform very, very well and keeps those tensile stresses that want to break the material well below the limits that we wound up establishing for ourselves. I think in the future we could refine further, but for where we are now, at least as we're starting on this, the system has a lot of capacity and a lot of flexibility to take various loads. We also investigated localizations of stress at the connection points to make certain that as this wants to twist and rotate and break, that it's not going to have a localized breakout at the ends of the system, which, as you can see, we use a threaded or sleeved anchor into the internal parts of the terracotta to kind of help distribute that stress more. And we'll talk more about the attachment systems a little bit later in the presentation. I think who's next on this?
Yeah, just some of the photos and a video moving around it. It starts to show how that form gives a really dynamic quality to it as well. Interacts with the light really nicely, and you encourage you to check it out afterwards as well. And the views behind it, I think, are quite nice as well. So, yeah, and the next component of the system is the glaze, and Kevin's going to walk us.
Yeah, Kevin Canoply, UNStudio. Thanks, Justin. So Justin and Jake just went through kind of the first pillar of the presentation, which is how the form kind of affects the carbon footprints of building through things such as passive cooling, etc. So the second pillar of the presentation will be about the glaze and how does the glaze actually contribute to the performance of the building, specifically by reducing operational carbon. So when we look at kind of a typical terracotta system, or kind of what we've been introduced to up to this, I guess, up to the moment of the workshop, is how the glaze of the terracotta system already contributes, especially to the lifespan, the ability to clean the facade system, and also being able to actually act as an integrated finish. So what we weren't seeing is actually how, the extra steps of needing to add glaze to the system, the efforts and kind of, I guess, the materials that need to go into that. We want to ask the question of how can we, leverage that to actually also improve the performance of the system. As we mentioned before, it's an integrated system and it should be leveraging it in this sort of manner. So similar to kind of the first pillar of what we went through of taking the inspiration from WasI Tower, we also took inspiration from a previous UNStudio project for developing the glaze. So the coolest white is development from 2019. It was, again, an industry collaboration of Monoble Paints in Europe. And essentially, it is a high solar reflectance paint meant for metal substrates. And as you can kind of see with the video playing there on the bottom right compared to the image on the top right, this paint is actually working to cool the surface of the buildings. And obviously, the reasoning for this is to reduce urban heat island effect, but also operational kind of demands within the building for cooling. And so when we kind of combine this with our form making that we went through previously, we start to see this interesting thing happening with the twist where there's these different angles and kind of faces that start to expose to different orientations because of how the material and the geometry is working. And you kind of see in this UNStudio project on the right here from 2008 that different vantage points and different contexts can actually start to have different I guess responses based on, you know, the side or the kind of face of the material that's actually facing outward. And so with that in mind, we kind of started to think about, you know, can a terracotta piece that typically, you know, the backside of you don't see it sitting against the interior of the facade, the cavity, can that, because we're now moving to a fin system where this is all exposed and it can actually be viewed, can we have a double-sided system? So I'll try to go through these quickly because I think they're quite important to mention. But you know, we have the typical system, what we're trying to do, where it's one side it's a finish, and then it's also providing high solar reflectance. We had questions about how, you know, being able to view this fin from the interior. Could we have a finish on the interior as well that's reflecting into the interior, as I was saying? You know, a lot of different precedents about how additives or even paints are added to certain facade systems to aid with pollution mitigation and capture. Can water be run whether inside systems or on systems, which we'll hear about later for sure, in terms of being able to facilitate evaporative cooling. Some interesting explorations about how can we actually join multiple terracotta pieces together, and the backside actually acts as a structural membrane that holds them all together without mechanical fasteners. And then ultimately what we're aiming for, of course, is the integrated product, you know, where kind of a lot of these different factors are coming together. So many thanks to Andy over there for helping us a lot, you know, actually bring his knowledge about what's out there in the industry and kind of what's actually in the market and can be scalable to produce all these various sort of glazes. So I'll try to go through them again quickly, and Andy just yell at me if I say something wrong about all these very chemistry-oriented names. But Ultrax is basically kind of a very commercially available white pigment that's typically used in, let's say, sanitary products like in the bathroom to make something super, super white. And so that's a pigment that's very readily available. Soldalit is a mineral-based post-applied paint that bonds to masonry, but also ceramic products. And Andy tested this for us and saw that it was actually working quite well with the terracotta. The specific one in test 2 had a titanium dioxide photocatalytic additive, and that was actually meant to help improve the cleanability of that surface. Barium sulfite, similar to titanium dioxide, is a photocatalytic material that again works, has a very high solar reflectance. Yeah, that also helps to improve the cleanability of the surface. Solidate Coolit, as the name implies, is similar to Glaze Test 2, where it's a post-applied finish that actually is meant to cool down masonry systems. And then we get a range of control samples to compare these two. So Glaze Test 5, copper green metallic, we were trying to just see. So the first 4, of course, we're trying to just make really white pigments with the intention, like the coolest white paint, that this would reflect a lot of sunlight and essentially cool the system already. But what we try to test kind of on the bottom 3 control pieces were also with the copper green, could we have a really, really kind of lustrous and shiny surface? And does that actually impact how much sunlight's being reflected? And of course, an unglazed clay body, seeing how that's performing. And then the bronze metallic is essentially trying to create a very dark glaze and surface and try to see if that actually increases the amount of heat that's being retained and absorbed. So I'll pass it over here.
Thank you, Kevin. So we decided to science this a little bit. This is the setup that we've been working with this past week. What you see, is there a pointer? I'm going to wreak havoc here now. Yes, just what you see there, that red gauge there, that's a thermocouple, which gets attached to the front and to the back of these samples. So we're going to show you just like a subset of this because there's more data than we have time to talk about. And also, obviously also, as you can, you know, there are scientists in this room, and I'm sure you have opinions on this, on the experimental setup here, but this is a two full spectrum UVA, UVB 150 watt lamps, the kind of ones that you use if you have a reptile at home or something to heat them up. And the basic setup of the experiment is to heat with a thermocouple front and back, and check that also with a regular, just like point and shoot laser thermometer. The starting temperature, the temperature after 10 minutes of heating, and then the temperature after 10 minutes of taking it out of the light and letting it cool off. And interestingly, well, with a thermal camera, you get sort of predictable results, right? You start cold, then you go up to something warmer, and then after 10 minutes, no sample gets rid of all its stored heat. So that's sort of the hinting at the urban heat island problem in thermally inert materials that we're already aware of. Now, what's interesting is that when you compare some of these samples that you see over there and some of the ones that Kevin just showed before, we just picked 4 here for sort of the sake of expediency. And these data points, it might be a little bit hard to read. I apologize for we're better at some things than we are at Excel graph drawing. But what you can basically see at the top left is that if you do what I just described to an unglazed tan body, you start at, this is centigrade, by the way, so the steps are about half of what Fahrenheit would be, but the relative situation is the same. You'd start around 25, which is the room temperature in that little room that we were in. After 10 minutes, you're up at 35 degrees by thermocouple. You're up at 40 with the laser thermometer, and then after another 10 minutes, you're down at those numbers you see to the right, at the 30.2, 29.6, 28.5. So they sort of converge again at the end, and not all of the stored heat is gotten rid of. Also, predictably, the laser thermometer gauges, measures something much higher than the thermocouple, because one of them is in direct contact and the other is not. But when we then go to a dark, just the darkest of the samples we have, we see that you go up to over 45 degrees and down again to something which is further away from the starting temperature. So this is also kind of predictable. We know that dark materials do this, and this experiment also should be repeated with where we can take into account, the actual reflectance of the material and the sheen of it. But we did what we could this week. Over here is that solid coolant that Kevin mentioned as a sort of comparison, right? You see again the curve sort of goes up and then it goes down. And quite interesting, do we think at least, the finish that we have on this mock-up here starts from the same room temperature. It goes up to significantly a less maximum temperature after the same time of heating. But then quite interestingly, it actually goes down more again, whereas this one up here, for instance, had stored relatively more heat and releasing it more slowly. So this does, at least provisionally, this here does both of the things that we were hoping, which is reflect away more of the it heats up less in the first place, and it also cools off more quickly, which is kind of two of the things that we want. And so you can see also like the light really plays in an interesting way on this, and obviously having a flat sample under a terrarium lamp and having it in the sun are two different things. So we did like a super quick and dirty check, just what would happen if we just compared the front and the back of this with the carbon steel brick that it's standing on. And I know this is a little bit hard to see actually because it was like full sun on top of that gauge, but basically what it tells you is that the steel, predictably perhaps again, but the steel is much hotter than the terracotta. It heats all the way through, almost the same temperature front and back, whereas the terracotta has a much cooler back than it has front, even under the same sunlight incidence. And this is sort of just a quick kind of thermal imaging to see, like, the blue there's like the back of the terracotta, and the red and the orange is the steel, and and the person also predictably. And that's it for that. That's for you. Thank you.
So we're gonna go and talk a little bit now more about how we are tying back into the building structure. And we took our study back into and integrated it with a typical curtain wall system. We compared it with the curtain wall system that's used on the WasI project so that we could have as close to a one-to-one comparison and see how much we're improving. But ultimately, the reason we wanted to go back and kind of tie this into the overall wall is that it's all well and good if we can improve the embodied carbon and the performance of the outboard system, but if it requires a massive steel column inboard, it's really not going to save you something overall. So we wanted to see how it comes together. And so just to start, it's just an exploded view of what the original WasI detailing system looks like. I'm not going to spend too much time on this. I'll focus more on our system, but just so you can kind of see, there's a built-up frame with everything put together on it, and these were lifted into place and attached to the building. For us, we went through a bunch of iterations. As Kevin mentioned earlier, we kind of played with different forms, but what we originally were looking at with this was something that allowed the terracotta to be formed a little bit more simply, but it necessitated more connection design. And ultimately, we were looking at trying to brace that middle area where there was originally a break in the terracotta, which introduced a weak point. So as we furthered our design along and we managed to push the terracotta to do more of the heavy lifting, we ultimately came up with the attachment systems that we showed before. So right now, the way that we have this detailed and the way that we have this assumed to function is that there is an internal carbon steel reinforcement frame that is in a curtain wall unit with discrete attachment fins that come out, also carbon steel. All of this would be painted. The central fin that is behind the terracotta but outboard of the curtain wall will be aluminum, most likely, but also could be a reduced steel depending on what we're looking for. Part of the reason this is important to tie this into the curtain wall is that since, once again, this whole system wants to act as a sail and sway, we really want to tie this into a diaphragm of some sort to help stiffen this from a lateral movement, which we'll show a little bit more, again, when I show you some of the results. But ultimately, by tying this into a curtain wall system like this, we're able to make use of the silicone to tie it into the glass and have this whole unit act together, which helps validate the proof of concept. But by doing all of this, what this does, and you can see the comparison of the materials that we ultimately ended up using, there's a very small reduction in the mass of the overall assembly once we account for include the curtain wall and the system behind it. But as you can see on the right image, which shows the global warming potential by assembly, so comparing the overall component elements, you can see we have a huge reduction in the global warming percentage that we're finding. And just to kind of refine that a little bit further, if you take a look here, this breaks it down further by material. So you can see really how much of the aluminum, how much of the metal we're really taking out of the system. I'm just going to show those two images again, but with more of the exploded view shown. So you can see same data, but just a little bit more clearly. And not shown in this image because it's hidden by the curtain wall is the steel vertical, but it is in there. It is accounted for in our analysis. It just is not able to be seen. So moving on to, again, proving that this can actually function on a building and that this will be something that we can make use of in a real practical application. We took those analyses that I showed earlier and we further elaborated on them, developing back a analysis that incorporates the sleeve connections, the plates, the angles, and everything going back into the vertical post that I mentioned about. And on the right, you can see that we analyze this with a pretty high degree of detail in at least how many nodes and structures we're looking at within the finite element system. I mentioned before that we would kind of talk a little bit more about the loads that we use and the way that we were applying this. So on the bottom, you can see a much more easily visible and understandable what breakdown of some of the load patterns we used. You know, straight on, a little bit unbalanced with a twist, or completely perfectly laterally acting as a sail. And what we can ultimately see from that, taking a look at how this is going to deflect and how this is going to move, really there is a lot of shifting that wants to happen. This whole system wants to kind of sway, but the majority of that sway comes not from the outboard system, but actually just the deflection of the mullion itself, which is why we want to tie this into the structure and allow it to kind of stiffen itself by using the diaphragm. And this is at absolute peak worst case deflection and worst case loading, which again, I do not believe is really realistic for this, but it was something to get us started. And so you can see here just the loads as these are being shared together. The loads on the right here are effectively what stresses we're inducing into the structural silicone, which comes out to be less than about 4 psi on typical curtain wall joint. So seems like it's something that can be used and is not going to really overstress or over tax an existing system or what it's being tied into. And we can see here some of the connection system and also some of time lapse of us putting these things together to show that it's something that is doable and installable by a bunch of amateurs who have never done this before.
Yeah, so those are the kind of three main tenets of our proposal. We also wanted to show you all some applications that we see this could be used in various situations. One of those is, of course, incorporating these vertical fins within a curtain wall system. So, how you have your terracotta that's thermal, recyclable, low emissions. You have, the coolest glaze, which is about solar reflectance, carbon capture potentially, and, just a beautiful finish as well. But also rounding out the system, how can you further reduce solar heat gain on the building, integrating a frit that plays with the form of the fin. We can incorporate the coolest white on all the metal and aluminum elements. And look on how that could be with a little kind of time lapse, show how the sun plays over it. We also have some views from interiors. How can this, in certain situations, might want to act more as a denser screening, but you're still getting plenty of view out as well. Getting exposure to that second surface. In other applications, it could be more of a low-rise facade, perhaps even on a building that doesn't have windows to still act thermally for that building. And again, showing how you really get those kind of oblique views out through the fin system, allowing for a nice variety of light within the space.
Okay, so we'll end it off just with the next steps. How would we kind of improve this amazing workshop that we were able to participate in, and definitely learned a lot along the way. As many of you have heard and saw when we were walking through the factory on Monday, there was quite a few complications and hurdles in terms of actually fabricating the terracotta pieces, of course, due to their size and weight, particularly with the drying. And there were some scenarios where the drying was not successful and ended up in crack and failure right through the middle of those pieces. And then also over the past 2 days, there was, of course, some kind of complications in terms of the assembly itself. And that was, of course, due to the specific geometries at the ends of the pieces that were sawed off in terms of accepting the connections to actually be able to mount these in and afterwards tip them up. So what we kind of want to think about in terms of next steps for this design specifically would be kind of a reduction of mass in terms of the webbing. But also, if there are other kind of processes or even a different connection design that could happen at the top and bottom to actually make that a lot easier to just kind of put together. Again, thinking about how this can be scaled more, especially in those kind of scenarios where you have a lot of this on a facade. In terms of next steps from more of a design perspective, we're kind of just bringing back some of these earlier studies here, thinking about, you saw in some of those renders and the diagrams for the LCAs, not LCAs, embodied carbon analyses, about how we're kind of stacking two fins on top of one another to actually create a floor-to-floor heights. But some of our early studies were considering again how we could join multiple panels together, or even have kind of a precast concrete system that would actually be able to allow the terracotta to within one kind of module actually span floor to floor. Again, we've been bringing things up kind of with some of the glazes and post-applied finishes that we showed about how they actually capture pollutants. So an air quality study could be kind of interesting if we were to choose one of these other glazes that actually had those finishes on it. One of the things that was in kind of a very initial brief before coming to ACAW was actually thinking about how the form and that texture this creates when it's actually multiplied across the entire facade, if that actually promotes slowing down wind and airflow behind and kind of around these pieces, and if that actually has a cooling effect on the facade itself. So wind or natural ventilation study could be quite interesting in that sense. And we kind of threw in the carbon capture word kind of towards the end of the presentation. Of course, that wasn't necessarily explored within the frame of the workshop, but we are aware that there's additives, let's say, that are added to concrete to kind of quicken or improve those processes about how a material can, sequester carbon. I think the reclamation of mining waste within the Ohio project in Ohio was quite interesting about how it actually sequester other materials to kind of limit their impact on the environment. And we chose the tan body specifically because it's the body that has the least amount of additives and the processes applied to it to get it to a certain color. So, thinking about how we still want to kind of maintain that, but different additives can be, explored within that body. So I think that's all. Again, thank you so much to the Boston Valley team, to Andy, to Andrew Cruz. It's so incredible.
Oh, question time. Are there questions? One in the corner here.
Hi, thanks for the awesome presentation. It's a really beautiful piece. For those of us who weren't a part of the factory tour on Monday, I'm really curious as to how these were dried to mitigate that warping and cracking you were talking about.
Yeah, I'm not even dressed up yesterday. We create specialty refractory jigs to support the pieces, so it's a technical process for us that we've put a lot of investment in terms of research and development to help ensure them. But it is, UNStudio and Walter P. Moore really did push the limits of what's possible with that in terms of
But the drying
scale, twist.
The drying itself
Yes.
is in like tenths and
Yeah, and drying is right. The pieces shrink. So clay naturally is going to shrink somewhere between, let's say, 5 and 15%. So across a length like this, that's like 6-8 inches. So that would start off here. So it's a quite a process, and it was very successful. I give kudos to our production team for being able to pull it off. But there's definitely, they pushed our limits.
Yeah, it's pretty amazing. Thank you.
Questions?
Hello. Thank you for the presentation. Very good work, and for the form and the engineering, of course. Now, really picking on the details, because you mentioned the project is in Dubai. So I was wondering, now thinking out loud, you might have thought already about it, or you might think it in the future, like for the Dubai climate, that there are sandstorms. Like for me personally, the form and the shadow would have already convinced me that you went further on the study of the glaze. So I was thinking, have you thought how the sandstorms would interact and maybe affect the performance of the glazing in time? Would it need some maintenance? And yeah, so that's what I was thinking.
In the existing WasI Tower that's almost complete, one of the reasons why it's darker material is because of that factor. If you do white, it naturally just starts becoming sand colored. So better to just control that aesthetic. But it's also, of course, a client request. We also like how it looks, of course.
Yep.
But it is, it's a trade-off between aesthetics and performance. But of course, yeah, like you said, the sandstorms will kind of affect that on both terms. Yeah.
And these glazes, as we develop them, we want to incorporate certain elements that increase cleanability of the surface. And, some of these experimental ones, we'd like to test that further on how that would hold up to sandstorms. And that could be kind of part of our further steps as well. That's part of our additional wind studies that we want to.
Thank you so much. It's a beautiful design.
We can still hear you. Is it green?
It's black and green and red. I think I held it down.
We can hear though.
Now it's off.
But they can't hear.
Oh, never mind. Oh, sorry. Never mind.
Thank you. So my question is about the colorants that you added to get the most refractory or the most cooling white. And I was wondering if you had considered like the metal, because most of these, or maybe all of the opacifiers or the whitening ingredients would be metallic oxides or have like metal contents, as well as like some of the ones that you mentioned that were more reflective. So I was wondering if metallic content, is considered as acting as a conductor rather than refractory, or maybe there's some metals that are more refractory than others. Is that something that you guys looked at all, or something maybe for the future to consider?
So I was hoping nobody would ask that. No, so that's a really good question, and we will readily admit that this is like very sort of kind of bare bones or quick and dirty investigation of that. But so if we take a parallel to like glazing technology, what the metal low E coating, low emissivity coatings are done that way for their ability to reflect in certain spectrums, especially infrared, because you're doing it so that you don't get solar heat gain through glass. I don't know what the direct translation of those same metals, noble metals, usually in terms of what they do in when they're incorporated into a glaze, but we certainly see like how it's significant, like the difference in how much they heat up, and that is just from sort of guessing. I don't think that is just a question of like regular sheen-based reflectance, right, of all of the light, kind of like a mirror or something. So there's something else going on there, which we will definitely investigate more. But what you just mentioned there is one of the sort of big questions that we have discussed with Andy, decided that we are going to try and, bite it off one bite at a time, so to speak, before we go to using like, mass spectrometry and things that would tell us more about those things. So that's a sort of an avoidant answer, but that's what we got right now. Sorry.
Definitely part of our next steps.
Yeah, thanks.
Okay, let me just take a quick look if there are people on the chat looking for a question here. You talked about the fins slumping into the shape against the mold. Are they developable surfaces or do they, I think, or do they show two-directional curvature?
Yeah, the form is actually derived by a twist, so it's a developable surface.
I think another way of answering that is that it's an extrusion that doesn't deform into an spot. Therefore, we could go back to the same flat shape as it once came. So,
Yep.
Okay. So, yep, it is developable. So very good. Okay, thank you guys.